Everybody, I think we're gonna get started. Hopefully the people online can hear us okay. Thanks everybody for coming, and this is an amazing turnout for summertime in Seattle. So it must say something about the incredible speaker that we have got to come and give a talk. So I'm really delighted to have Dean Feng here in town to speak to us. I'm going to say a few things about her, but one of the things that has been so impressive to me in watching her work has been this really cool intersection of AI and statistics, which I think is a burgeoning area in our field. And I think when I think about the people who are kind of at the leading edge of this, probably in the country, Jean comes to the very top of that list. So I'm very excited that she's here to talk to us about this. She's an associate professor in epidemiology and biostatistics at the University of California, San Francisco. She's a principal investigator of the Center for Excellence in Regulatory Science and Innovation. And she's also the data science project lead for the prospect team at the Chan Zuckerberg San Francisco General Hospital. I think I got all that right. Her work has covered a number of different areas. We were just chatting before we got started here on both computational biology and statistics applied to AI concepts. And I just want to say thank you to us and your talk. Thanks, Jean. Okay.
Somehow find an excuse to come visit every summer as of last summer. But yeah, it's great to be back. Okay, so today I'm going to talk about various ways that people judge LLMs. And maybe, that's not what I meant to do. Cool. Yes, so I'll just give a brief background on what we do in the lab. So half of our efforts in the lab is dedicated to developing new methodologies, usually thinking about how do we apply statistics to AI or AI to statistics, and the goal of making AI more reliable, particularly in healthcare settings. And then we work a lot with the FDA when we're doing this type of methodological research. And then the other half of our efforts is on deploying AI models, developing them, evaluating them, actually running it in the hospital. And we do it at the Zuckerberg San Francisco General Hospital, which is the safety net hospital of San Francisco. So there we also want to think about a lot of things surrounding equity and kind of the unique needs of these. So it's been a really fun experience kind of working at that intersection, and the best part are when projects kind of appear in the middle. And so both of these projects are a little bit kind of that flavor. Okay, so given that LLMs and AI has really exploded, I guess, I don't know, since 2022, 2023, our team has been thinking a lot about how do we deploy these types of technologies within the hospital. So I just want to give a background of like the types of AI tools we're thinking about and why I'm talking about judging LLMs. So this project at CSFG, we're working with the social work team to come up with ways to extract social determinants of health. And there's something like 22 different factors that the social workers are very interested in, given that we're a safety net hospital. A lot of our patients have these types of concerns that we want to make sure we're doing a good job of tracking. Unfortunately, a lot of this information is hidden in the unstructured clinical notes. Sometimes it feels like you're trying to find a needle in the haystack because usually it's not particularly well documented, and things also change over time. And it's a lot of work for social workers. So usually before they meet a patient, they try to go through all these records so that they're prepared going to the conversation. So our hope is that if we can summarize a lot of that for them, they have a leg up. Okay, so this was one of the projects. And then another project we're thinking about, or I guess this one, so I work at both UCSF and CSFG. At UCSF, like everyone's using AI scribes. I'm sure the Hutch is using AI scribes. But this one, there's a couple out there. I think this one is pretty popular. And obviously there's a concern like, are these things working? Are they saying, are they writing down the right stuff? We know there's issues where, like, for instance, if there's a patient in the room and someone accompanying them and the clinician's talking, there's like too many people talking, and then the AI scribe, like, who's saying what? Or AI scribes might say, I don't know, they might be missing a question mark, and suddenly a question becomes a statement. I don't know, all sorts of things can happen in kind of what gets summarized in the patient record as a consequence of using these types of tools. Okay, so these tools are very exciting, and they can enable kind of healthcare providers. However, because they have errors, I want to make sure the error rates don't increase over time, and we don't want to make sure these things are actually working. So in terms of like evaluating these types of technologies or monitoring these types of technologies, one of these two paradigms have emerged. I'm sure maybe there are more, but these are the two that I'm going to talk about today. And these two have kind of led me to like rack my brain for a long time. Okay, so the first one is LLMs judging LLMs, or LLM as a judge. How many people have heard of it? Some people, okay, that's fine. And then the other option, which is humans judging LLMs, which presumably makes sense. Okay, so I'm gonna start with the first project, which came out at AI Stats this year, where Patrick, my data scientist, got to go to Morocco to present this work, which was fun. Okay, so all right, what is LLM as a judge? LLM as a judge is a super popular technique that is used in industry. And here's an example of, on the Azure website of Microsoft, of how they would recommend you to use LLM as a judge. So they would say, okay, well, given that LLMs output freeform text is very hard to evaluate, you could either pay a human to go review every single text that comes out. Turns out that it is very costly. So why don't you just try out using LLMs to evaluate the outputs from another LLM? So the LLMs that they would recommend, and at least at the time this website came out, was like, okay, well, you can consider using like GPT 3.5 for 32K. Anyways, these are the different models, and then they would recommend like different metrics. Like you can evaluate things on groundedness, relevance, coherence, fluency, similarity. And then the prompts that they give, I think this was copy pasted from the bottom, but generally the prompts look like something like this. You ask your LLM judge, hey, look at this response. What do you think? Rate it on a scale of, say, 1 to 5. And so then it does it for each one of these axes. And so, like, people will use this type of LLM judge system and then, like, potentially use it to monitor the performance of their deployed model and see, like, oh, if the average quality rated by my LLM judge has been going down, like, maybe that would be a sign that something's going wrong. Anyhow, so this is super popular, but it also is like, if we're having LLMs judge LLMs, are we just like going in a circle and actually doing anything? And so my statistics brain was like really confused. At the same time, everyone is doing it. So it's like, there must be some value. It must be working to some extent, but something must be missing here. Okay, so just to simplify the problem a little bit more, I'm going to think about this problem within this specific context. So the other reason we use LLM judges is because we're trying to benchmark LLMs against each other. So there are websites like Helm, Holistic Evaluation of Language Models, which is hosted by Stanford, and many other companies and other nonprofits who build out these benchmarking websites where there are a lot of these candidate LLMs, that's what I'll call them. Sometimes the number of candidates can be like 30 or so. And then they are judged across all sorts of different data sets. Some of them might focus on like answering just like science questions. Some of them are like multiple choice. Some of it are like clinical questions, and where the answer is not just like A, B, C, D, but actually like outputting some sort of free-form text output. Or there's another example where it's like, how good are you at writing math proofs? So here's a theorem, and then you have. And so for the ones where there are free-form text outputs, it does become very hard to judge. And the people running these types of benchmarking websites, they are not going to go recruit a new human for every new model that gets released out. And so oftentimes they rely on LLM as a judge. And the great part was that one of my friends actually is a maintainer of this benchmark system. So we recruited him to help us on this project to think through the statistics. Okay, so here's the general workflow that we're going to be thinking about. We're going to assume we have some sort of benchmark data set. Benchmark data set is just a bunch of different questions that the LLM is expected to provide answers to. We have a number of candidates. Each candidate is going to provide answers to each one of those questions. And then you're going to have judges. And we're going to have, here I have two candidates. They are also going to act as judges. So along the diagonal, they are self-judging. And then there are also things off the diagonal. Usually we have 1 to 2 judges. We don't usually have like 17 candidates and 17 judges. That would be way too expensive. And then they are given a rubric of, say, like, score this thing from 1 to 5. Right, so then your goal is to come up with a ranking. You do not, let's just presume we're in a setting with 0 gold standard labels. This is particularly relevant in the monitoring setting where it would be very difficult to capture data labels long term. And we are obviously concerned about all sorts of biases that can appear. We know that models prefer themselves. So if like a GPT model judges a GPT model, it's like, yeah, that's a great answer. There's also position bias. So if you ask it to rank like answer 1 versus answer 2, if 1 comes first, it usually likes 1. It likes really long answers. That is a human trait as well. Okay. And then the questions of interest here are, 1, if we do not have gold standard labels, kind of just like, what are the theoretical limits to this system? Like, even if I had infinite data, can I actually figure out the true rankings between these LLMs? And then based off of our identifiability results, can we come up with some sort of practical recommendation in terms of like the statistical methodology and how we analyze data? Okay, and so as a person with a biostats degree, I was like, well, what have biostatisticians actually thought about already? And it turns out we've been thinking about this problem for a very long time. Oh, great. This book is from Margaret Pepe, where I believe chapter 7 is on incomplete data and imperfect reference tests. And I was like, oh, great, this is exactly what we're working on. We do not have gold standard labels. We have imperfect labels, which is from our LLM. And we're going to figure out how we're going to evaluate things using our imperfect. The slight difference is that a very common assumption in this setting is that, so I guess the classical setting of biostats is there's a diagnostic test, it's not perfect, but we're going to try to judge its performance. Or maybe there's a reference test and one that we're trying to judge. And usually you assume this imperfect judge is conditionally independent. And so you might have multiple of them, and then you can kind of decouple weights and customate whatever estimate you're interested in. The problem is if we actually have LLM judges, I'm very concerned that all of the LLMs are trained on the same internet data anyways. They are probably not independent. Okay, and then the other kind of nice existing work that came out in JASA in 1970 was just like geometric visualizations of 2x2 contingency tables. So you will see that everything kind of boils down to these beautiful pictures. And so for a while I was drawing like tetrahedrons and my husband was looking at me like, did Jean join a cult? All right, okay, so let's just simplify things. We're gonna think about just a 2-level scoring rubric. Like if you're just gonna judge an answer from an LLM, like accurate or not accurate, like 0, 1. And then we'll also think about 3-level or 3 or more, where then there's going to be like a Likert scale going on. Okay, so starting from the 2-level rubric. So kind of the key thing we're thinking about here is really this confusion matrix. So here we have the true score, of that answer given by the LLM, and then the actual score that the judge ends up giving. Right, so, and just for simplicity's sake, we know that judges can judge different candidates differently. Like if it likes itself, it's going to do something else. If it sees Claude, I don't know, maybe it's like an adversary. It's like, oh, I want to downrank all of those, get these super confused on those. Let's just for now, let's suppose strong constancy, which is just that the judge's confusion matrix is going to be constant across all candidates. And so if we look at the columns here, this is saying, okay, how often is the judge outputting a particular score given this true score? So theta 1 is given that the true score is 1, and then theta naught is given the true score is 0. And then so we can just draw this, right? So everything actually has to fall in the simplex because this is a conditional probability distribution. It's going to sum up to 1. It must fall in this line segment. So theta 1 is going to be somewhere down here, and then theta naught is somewhere. Okay, we don't actually get to observe theta 1 or theta naught because we don't actually see the S stars, the true scores, but we do see the observed scores. So the observed scores are how often does the judge assign kind of each of our candidates, candidate K, 1 versus 0. And so this must be a mixture of theta naught and theta 1. So it must be somewhere in the middle. And just by look, and so I guess like, if this candidate has more of the true score of say 0, it would be closer to this end. And like, so if theta 2 has more of theta 1, it would be closer to this end. And so just by like looking at this picture, it would be very natural to say, okay, well, our candidate K equals 2 must be better than candidate K equals 1. And it really doesn't matter like where theta naught and theta 1 are. They are just like ranked on this line. Okay, so then the nice thing is, okay, like assuming this strong constancy assumption and assuming that our judges are not like completely adversarial, like we just need it to be better than random. Then we can just look at the relative positions of these observed scores and conclude one is better than the other. And the other nice thing, so before, to actually go from this setting where there's only 2 scores to the setting with like 3 or more scores, there's a concept called barycentric coordinates, which perhaps many of you have heard of already, which just says that the prevalence of, I guess, like if you want to know like what the proportions are between, the proportion is between, I guess, the true score S star equals 1. Like how much of a mixture is this of theta naught versus theta 1? You just need to look at the relative distance. So the proportion, the probability that the true score is equal to 1 is just this distance over this full distance here. So theta naught to theta 1 versus theta naught to theta K equals 2. Okay, so then that's in the 2-level setting. In the 3-level setting, this same barycentric coordinate system still exists, but rather than talking about the proportions, the proportions for the line segments, we're talking about the relative areas. So now we're saying, okay, the prevalence of the true score of say 3 is actually how big is this subtriangle compared to the rest of the subtriangle. Okay, so then if we just think about these triangles, then like you can come up with visual proofs to yourself that it's very hard to actually rank things properly because the middle triangle, we don't actually know where these endpoints in our triangles live. It could rotate in all sorts of ways. And so once it starts rotating too much, the ranking small triangle areas, their relative ordering can start flipping, right? So now rather than this one, which said, okay, this one has This one is close, this one has the bigger triangle, so it has more of 3 compared to this one. Now this is say, okay, well, this triangle is actually smaller than that triangle, so this one has less of 3. Okay, so then like, if any rotation is allowed, then in general, it would be very difficult to actually rank these candidates against each other. So our general conclusions as a consequence became, like, you have identifiability in this 2-level scoring system under pretty weak conditions. I mean, there are still assumptions, but like weak-ish is what I will call it. But then in this 3-level scoring system, and I'm sure, and you can extend this to even higher levels to, it's generally not identifiable. And so this was actually known by the LLM community, but they were thinking about it less from a statistical perspective. I think they were thinking about it more from a psychometrics perspective. It's just like very hard to align people and LLMs on a Likert scale. It's very hard to pick between 2 versus 3 versus 4 versus 5. And so there's kind of this like group of people who call themselves like the LLM evals people who release like blog posts and Twitter posts who are like all about saying binary evaluations are better than Likert evaluations. And we're like, I guess we have proved your point to some extent. Okay, but then like there are reasons why people use Likert scales. So like, is there something they could do? And so generally, it would be very hard to rank these candidate LLMs if you're in this Likert system. But if you do have some prior knowledge, like there are certain triangle locations where you're like, that probably doesn't make sense. And so if you can inject that prior knowledge, then you might actually be able to. And so we came up with a Bayesian model. I'm sure you can come up with other Bayesian models, where you can add in like, we can talk about, okay, can we relax some of our assumptions? We assume like constant behavior across the different candidates. We can actually think about relaxing that. How much would relaxing it affect our final rankings? And then we can also have priors over how good our judges are. So basically where those triangle vertices are exactly. And then if you vary the priors for the constancy assumption, for this judge like quality assumption, then you can basically conduct sensitivity analysis. And obviously because you have a Bayesian framework, then you have uncertainty quantification. Okay, so I don't really feel like jumping through all the details of this Bayesian model. You're welcome to read the paper and we can talk about it offline. But I'm going to show kind of the results we got. Okay, so we ran this on 5 different data sets. So GPQA is a multiple choice thing. We're using the multiple choice stuff so that we have some gold standard ranking that we can check our methods. So MMLE is another multiple choice one. And then these 3 are free-form text answers. So there's writing math proofs, summarizing news articles, and then just multi-turn conversations where it's like, help me plan a vacation, and then you write da-da-da. Okay, we ranked 17 candidates, courtesy of our friend Yifan. And we had 2 judges, GPT-4o mini, Claude 3.5 Haiku. These are a little outdated, hence they are smaller models. Or I guess when the data set already had a judge, we use those. Okay, so what you're seeing here is the Bayesian method is our method here on top. We also have other simple comparators that are more commonly used. So often people just use a single judge and just have it rank everything. Or you might have 2 judges and then just take a simple average. Bradley Terry is where you do a bunch of head-to-head comparisons and then fit a very parametric model. And then you could also think about bootstrapping. So maybe like a simple average, after you have 2 judges judge everything, you actually do a bootstrap. So to get some sort of confidence interval. The concern with all of these methods is that they are basically taking the judge scores at face value, and they're thinking a lot about the uncertainty from sampling. but we're worried, I think our method is slightly different in that we're worried about, it's not just a sampling error, it's that the judge scores themselves might not be correct. So I think if you're familiar with, the AI literature likes to refer to this as aleatoric uncertainty versus epistemic uncertainty. Aleatoric is like sampling error, and then epistemic is just like unknowns kind of thing. So our method is like somewhat unique in that it's really dealing with the second one in addition to the sampling error. So you can see, so for these different data sets, correlation, so the correlation is measuring how correlated is our estimated rankings versus the true ones, and then this is coverage. We're aiming for a 95% coverage. We're getting the 95% credible intervals from the Bayesian method, and then the other ones are outputting some sort of construct some sort of confidence interval. I guess these don't even construct a confidence interval just because this is very common. People are happy with a point estimate sometimes. Okay, anyhow, you can see that our method achieves higher correlation, not that much higher, but somewhat higher. Coverage is substantially better because it's dealing with that additional source of uncertainty. And then you can start to visualize things. So you can do sensitivity analysis by varying the prior, and you can see like, oh, okay, or this is like correlation with our originally estimated rankings and how much does it shift as a consequence when we kind of vary our prior. Some things do not shift at all, so this y-axis just doesn't change. And some data sets, if they, I forgot which hyperparameter switch. This must be constancy assumption. On certain data sets, if you weaken the constancy assumption, our estimates will drastically change. So this is like, well, what if our judge is being inconsistent in its behavior when it's judging everyone? That would obviously be very confusing trying to rank stuff. And the other nice thing is you can visualize kind of the estimates. So this is our triangle with the true scores, basically plotting out the vertices of our confusion matrix or columns of our confusion matrix. And so like on a data set like empty bench, you can see that everything is super well separated. The triangle is pretty stable. Like our rankings are probably going to be quite stable in that setting. Whereas in this setting, writing math proofs, everything is, I mean, there's a lot of candidates, they're all kind of close to each other, and the triangle is like moving all over. So it's very hard to actually rank things properly here.
That's why you think those are such different use cases like that? Why you see such different?
Empty bench is honestly a very simple data set. And it might be, I forgot the exact set of models they ranked, but it was like planning vacations. OmniMath, they took like really hard math Olympiad questions. And so they also even had it ranked from like, I don't know, it's like Putnam and so I think. And it might also be at that point in time, the math, like writing math proofs was not a strength of AI models yet. I think they are probably a bit more clustered at that point. Okay, cool. So that is judging LLMs. Oh wow, this is like perfect time. So that's one way that people use to actually evaluate these models. Now I'm going to switch gears and talk units. Oh, yes, before I switch gears. So summary. My conclusion for whether it works is like kind of and kind of not. In terms of like methodological recommendations, it's like you should understand that there are potential biases and you should try to model that bias by using, for instance, some sort of Bayesian inference that acknowledges your uncertainty about the quality of the judges. And indeed, you should probably favor binary scoring systems.
This is something you're interested in. I guess my understanding is that this product is based on just ranking a couple different scoring algorithms, but it doesn't really tell me if either of the scoring algorithms are good, right? Or sorry, if either of the I guess answers that you're getting from AI are any good. Maybe one is like a D and one would be given F, right?
Yeah.
So I don't know if that's anything that you're thinking about. So like. It's not quite a measure of quality, it's just like a measure of relative quality, but I don't know really if we thought about getting to like an absolute measure of quality as well.
I think from the Bayesian method, it will give you uncertainty quantification about like prevalence. I mean, given that it's a Bayesian model, it'll report anything to you. So you can actually get that, but I think the rankings are much more stable. So those are just the easier things to estimate. So that's why we focused on that mostly. But yeah, well, I'd love to move to the setting of being able to actually estimate things on an absolute scale, because oftentimes there's only one model I'm worried about, because I'm maybe only deploying one model. So what are you gonna do there? Yeah.
Since you're kind of using the LLM to judge the LLM, so I'm kind of wondering that fundamentally, when you actually do find there's some kind of disparity between two LLM models, for example, is that because of the source data they use, they're different, or is it because of the algorithm, the train those LLM be different?
Probably a mixture of everything. On top of that, there's this, I forgot the exact name they came up with it, but there's this hypothesis, this running hypothesis that it is harder to generate answers compared to validating answers. So even if you took the same exact LLM and told it to judge itself, there's a hypothesis that it probably does it better at judging than generating. So like the judgment might be okay.
So since we don't in the actual sort of settings, I mean, I'm not sure the benchmark you know the absolute truth. You maybe have some good reference, but in general, there's no absolute truth. But simply that the consistent inconsistency, does that give you a confidence that if we would actually the conclusion that the difference between the methodology actually mean anything?
Can you rephrase that?
Well, the rephrase that basically, well, in absence of the absolute truth,
Yeah.
right? So when you actually have comparison, for example, the one particular area judging another one, and then you good or bad, I mean, the percentage is 85 and 90%, and you've been showing some kind of coverage probability as well. But did that mean something?
So for this one, for the results here, we very explicitly made it such that there is a ground truth.
Okay.
So like the GPQA, MMLU, both of them have multiple choice answers. We just like masked that when we were doing.
I see. Okay. So therefore, those numbers is actually the actual meaning.
Those are absolute truths. And then for these three that actually have freeform answers, there's a reference answer that is freeform. And so this is like a little bit more approximate, these three, because it's like for the answer outputted by the LLM, how closely does it align with the reference answer? So like if there's a true math proof, then we compare it against like what was actually generated.
Sorry. So I guess it's a philosophical question in the sense when if you're suggesting that binary judgments are the better way to judge an LLM, in situations where judging an LLM requires just a binary yes or no, is it even required to be judged, or does it improve the quality of the output if all you're judging is a binary output?
If the LLM only
outputs
outputs
the LLM, if all you're judging is
I don't know.
okay.
Yeah, it's like if you are judging yes or no, that is basically the same model judging itself, right?
Yeah.
So I have not figured out the answer to that question, or I haven't figured out how to formalize it, but yes, I have not. Yeah, it's complicated. Okay, cool. That's LLM judging LLMs. The other thing that has had me scratching my head is humans judging LLMs. And you might think, oh, well, like if you had gold standard data from a human who could just tell you if the LLM answers are perfect or not perfect, like why would this be such a hard problem? I will tell you why. Okay. Okay. So there's a lot of papers on how you're supposed to evaluate your AI deployments. Like some research papers will talk about like red teaming or like generating potential test cases for your LLM. So in this specific paper from Microsoft, let's see. So you have your LLM. Okay, so you have like maybe some benchmark. I guess they don't necessarily need to even have test cases. They might have run something on a few test cases, And then depending on what it does well on, or what your LLM does well on, or what it does poorly on, maybe an LLM helps suggest some test cases. Then the user filters and organizes and then decides what thing you want to test your LLM on next. So there's this like adaptive procedure that is being recommended. Oftentimes in practice, I don't think actually people, this is like what researchers recommend. I don't think this part typically exists. Is just you test it on some test case and the human's like, oh, I feel like I want to test this one next. I'm gonna test it on the next. There's a YouTube video, I think, where they were interviewing the creators of Claude Code. Let's see. We tried really hard when building Claude Code to build product evals, but honestly, it is like so hard to build evals, and by far the biggest signal is just the vibes. Yeah, so it's just like vibing. It's like, okay, I think it looks pretty good. All right, it's good. And to some extent, it kind of works because LLMs are just that good, right? Like, if it got like 80% of the stuff wrong, then we'd be like, vibes probably are not going to cut it. But it's getting like more than 90%, right? So then you're like, okay, maybe I can get away with this. By far, the thing that I see the most is what is described in this Twitter post, which I think this is a rebuttal to all the LM eval people who are like, you should do evals, and Twitter is like evals. But then when I talk to anyone at a big lab or even a startup, I've talked to many people at startups, they'll be like, here are the 10 prompts I tested. I read them every couple of checkpoints. Or it's like, I guess I've had friends where they'll show me, I'm testing out my AI system. I have these 17 different use cases. Like these are examples dropped from users, and it passed all 17. So we're good. Like, okay. Does that make sense? I don't know. And like, yeah, exactly. Because LLMs are so good, like maybe passing 17 is good enough. I don't know. And they were adaptively selected, so like, I don't know, maybe that's a better way of testing. Okay, so the question I'm particularly interested then is, we have some human that's going to read the output, and let's just say our human can actually output like the gold standard label, looking at the answers like, oh, this is correct or not correct. And then the human starts thinking about, okay, is there a harder test case? What types of things is this probably going to fail on, or is there some suggestion of where it's failing, so I can pick out more test cases to see if that is an actual failure mode. And the thing that's also a little bit confusing, not only on top of the adaptivity, is that usually the number of observations they're looking at is very, very small. And I think that this paradigm has emerged because there are kind of two groups of people who work on LLMs. One is like the computer scientists, which to be fair, I guess I did get a computer science degree, so I understand. Like there's unit testing where you like write 10 or so unit tests. You're like, okay, if I put in this specific use case, does this happen? And it's usually when you write software, or back in the day when you wrote software, it was deterministic. So if it passed those 10 unit tests, you're like, okay, it probably works pretty well. The problem in our setting is that LLMs are not deterministic. And just because you passed a few tests doesn't mean you can, there's probably some subgroup you haven't tested that might have very, very different behavior. So you haven't like fully tested the thing. And on the other hand, you have statisticians, or like there's some statistical training in a lot of AI practitioners. This is actually a figure out from Purdue. There's a blog post and white paper preprint from Anthropic on like how to properly test LLMs, and they were vouching for a more statistical view where they're saying, okay, let's view things as some population of questions, and then we're sampling questions from that. But this is, whatever this LLM adaptive testing thing, it's also not that either, right? We're not, one, our sample size is really small, and two, we're adaptively selecting it. It is not IID. Okay, so then the questions that I was struggling with, and our team was struggling with, was if humans are going to use an adaptive testing approach, what null hypothesis are we even testing? I don't think that was even very clear. And then under what framework can we view adaptive testing as kind of making some sort of statistically rigorous claim. And then given this, like, what suggestions do we have? Okay, so to just present some notation here, so we have our LLM queries. I'm going to annotate. I'll denote with X. We'll have gold standard scores, which I'll use Y to denote. Let's have S denote a subgroup of LLM queries, and then let's say the average score in a subgroup, I'll say the V of S, value of S. And then when I say failure mode, it means that there is a subgroup, maybe of sufficient size, like at least prevalence, like 5% or something, where this average score is below some threshold. And then the question is like, what null hypothesis are we actually trying to test here? And this is what this is the one that I felt like made the most sense for the paradigm that people were thinking about, which was kind of like a more omnibus null hypothesis that said, where the model is like, I don't have any failure modes, try me. And then it's like, okay, well, the auditor will be like, fine, let me I have some strategy in my head. I'll denote that with tau. And I'm going to guess subgroup, say ST. I'm going to sample from this subgroup, see how you respond, and then you reveal the score back to me, or whoever revealed the score. And we just do this cycle over and over again. And so this null hypothesis seemed to be the most relevant. And so you can imagine, like, as the auditor is getting more information about how the model is doing, it might be the auditor might be picking out different subgroups over time, and hopefully finding if there is a subgroup that it does poorly in, the auditor will hopefully kind of zone in on that and then repeatedly sample from it to prove that there is a failure. Okay, so then how do we actually make this statistically rigorous? And I have to thank my data scientists for suddenly getting an interest in e-values and testing my betting. And I was like, wait, that's solving the problem. There's a bunch of people, Aditya Ramdas, Glenn Schaefer, who've been working on this kind of e-values kind of testing framework, or like this testing my betting framework. Where the claim is that if you want to test a null hypothesis, you can think about using this thing called the e-value or an e-process, where you make a bet in the first step, you reveal some win-loss, and then you get a return. And under the null, you just have to design this game such that there is no winning betting strategy. If we really want to go into math, basically the E process is basically a martingale or upper bounded by a super martingale. So every time your expected return is 0 or no bigger than 0. So if you keep playing this game, like presumably your returns do not increase gradually. But if the null is incorrect, then there should be a way to win the game. Okay, so then there are a lot of E processes actually out there, some of them very, very classical, like SPRT or likelihood ratios. There's also kind of from Larry Wasserman, he published a thing called universal inference, which is a little bit like a generalized likelihood ratio. There's also like change point detection methods that have also been kind of reframed as an E process. And so we can now go back to our picture and draw this as an E process. So the bet is the auditor picking a subgroup. They sample from the subgroup, we get our response, we reveal a score, and then we got to update our E process. And so the actual test statistic that we're going to be monitoring is whether or not this E value is going to shoot up beyond a threshold. And under the null, our E value should not, our type 1 error is guaranteed at a level of alpha if it exceeds a threshold of 1 over alpha. And the nice thing about E processes is also that everything is finite sample, which is also really important given that we do not have a lot of observations.
Is this true across multiple subgroups? If you're trying to do that, is that guarantee across multiple subgroups?
Yeah, so that's why the null hypothesis is designed specifically as an omnibus.
It can be,
I'm gonna claim, the model is going to be claiming there is no subgroup that you can ever find.
I
So
see,
test,
okay.
test me as hard as you want.
okay,
Okay, so that's like one version of the game. But this is a very sad game because the only outcome of this game is you lost. And if you fail to project a null, we still don't know what's going on. And it would be great to win the game, like, aha, my model does have no failure modes. And so the other thing we thought about is there a reverse game? And so the null hypothesis that we settled on that seemed reasonable to actually test is the auditor saying, I can find a failure mode within m tries. It has to be a finite number of tries, because if you let the auditor try forever, we would never be able to show that the auditor is wrong. Okay, so then the reverse game is the model has to be like, okay, given my, say, fixed model, I'm going to bet my generated response is good. Be able to score, we update our E process, the auditor can ask whatever subgroup they want, and then we sample from the subgroup, and then we resume the cycle. And then same thing with the E process. I guess, okay, so this is just the subgroup score. So if your auditor is continually sampling the subgroups that are doing well, then we would end up concluding that you've passed the audit. Or I guess from the E value picture, it would look something like this, where by the end of this process, you have still failed to actually, wait, no, I should actually exceed this, sorry, I drew this incorrectly. So the null hypothesis is that the auditor is saying, I can find a failure mode, and our E value should end up rejecting it to say that the auditor is wrong. You have failed to find a failure mode within m tries. Okay, and then you would conclude I have passed the audit. Okay, so there are two games being played. Managing to prove the model wrong means there is a failure mode. Managing to prove the auditor wrong means that you pass the audit. We call these dueling hypothesis tests. And if we think about things asymptotically, actually it's just one game, assuming your auditor is very, very good. Like if your auditor is guaranteed to like learn the bad subgroup within, I guess like if you let multiple things go to infinity. So you let the number of tries also go towards infinity. Then if your auditor is asymptotically consistent, is guaranteed to find the failure mode if it does exist, then they're actually playing the same game, and their test statistics are kind of basically like inverses of each other. Okay, and so then it's a nicer kind of thing that you're testing is there is some failure mode, and just prove that it is not true. So then your model is indeed perfect. This is a little theoretical though, because in practice, probably your auditor is not that good. But in general, the practical takeaway would obviously be get a strong auditor. Okay, so just to kind of summarize things. So in terms of answering the questions of interest here, we've reframed everything in terms of these omnibus tests, and there's kind of two of them. Sometimes they're the same. To actually, the statistical procedure we're going to use is pairing everything with an E process, and this testing by betting framework. And then we can just build off of what exists in the literature and kind of extend things here and there, where we've kind of thought about these different E processes, thought about likelihood ratios, universal inference, and the Sherman-Roberts kind of change point detection method. Okay, so then we actually tried to run this on some semi-synthetic benchmark data set. So taking our GPQA data set from previous, we generated data that looked like it so that we can do multiple replicates on various data sets. This data set has different kind of subgroups, some across different science fields, some across different education levels. Our failure mode is defined as accuracy less than 0.85. And in our first setting, let's suppose our auditor has access to an unlabeled data set that it can actively sample from, or I guess it can actively choose whichever observation it should label. In practice, we're actually implementing this auditor as a deep learning model because I do not have enough humans to run enough replicates to test out power. And so you can imagine basically like the sequence of questions that the LLM might be sampling might be coming from these kind of different intersections of these domains. In practice, it's basically looking at the question embeddings and then deciding like, okay, is defining a subgroup based off of the embeddings of the questions, sampling that. Okay, so then in terms of the results, here the top row is there's a big performance deterioration in one of the subgroups. There's this medium deterioration, small deterioration, and that there are no subgroups that did poorly. This model is like beautiful. So we managed, and this column is how often we end up rejecting the models null. So we end up saying that there is a failure mode. This is how often the thing ends up inconclusive, and then this is how often we would conclude that the model has passed the auditor. So if there are no failure modes, all the methods that we've tested out include like, okay, you've passed our auditor, and I guess in this case, the number of samples it needed to label can vary from like 100 to like 200-ish. And we capped it at 300 observations. So that's why sometimes you have inconclusive things. Among the different methods we tested out, these two are just very simple methods. So stratified sampling, so just sample evenly across these different strata. Pre-learned is like, suppose we had an initial small data set, you learned something, and then you kept that sampling strategy fixed afterwards. You have your oracle, which just knows everything, the likelihood ratio, Sharer-Roberts likelihood ratio, all the variants of the e-processes basically down here. And so if there's a big performance drop, all the methods find it, and you can actually manage to reject the null hypothesis, our model claiming that has no failure modes, with very few samples. I think some of them go down to like 20 samples, and you can already like conclude like this thing doesn't work. And so that actually does give some credence to what people are doing, which is they look at 20-ish samples to be like, does this thing work or not? When there are smaller performance decays, then you presumably need more samples. If you have, obviously, if you're the Oracle model, you're fine. But for everyone else, you do need more samples. And among these different methods, basically this change point detection method combined with a likelihood ratio and a universal inference, that one does the best in terms of sample size and power. And then we've done like similar other experiments that I do not think I want to. I'll skip this one. I want to get to the real world experiment here. So going back to the first slide that I showed, where we had our AI application extracting SDOH, social determinants of health, from clinical notes. What we wanted to know is, okay, can we actually use this procedure and re-audit the model we had developed, or actually just the LLM prompt that we created. Okay, so then like looking at the social risk extractions, this was done across all these different domains. And our original evaluation to see how good our model did across these different domains required 22,000 or 2,200 annotations. So we had a number of patients, and then each of these patients would get annotated with yes or no's for all of them. And so taking this pipeline and applying it to this example, it very quickly started upsampling certain areas that the model was doing poorly at. So this is the true correctness rate of these different type of attributes it could be extracting. And then this was how often our auditor was sampling it on average. And so it would upsample the things that was doing poorly. This is an example plot of what our e-processes would look like, where it would end up rejecting because there were indeed subgroups or certain attributes that did very poorly. And then, right, among the replicates, then this kind of last method ended up having the most power. And then the number of samples is certainly much smaller than 2,000. So you do not need to annotate 2,000 things to actually conclude that there are some issues with this model. Okay, so
If you go back to the previous slide, so it seems like there are some areas where, at least it looks like from the dots, that it is kind of working well, and then there's subgroups where it's not. This kind of universal null or global null doesn't kind of distinguish between those.
Yeah.
Have you thought about like how you create a hierarchical null or something that allows you to
Yeah.
To do a subgroup analysis here and you
Yeah.
know, which ones it's kind of okay for and which ones it's not okay for.
I have not. That would be interesting. Actually, Conway has done a paper on, not on adaptive testing, but like creating a ontology or a hierarchy for like how failure modes relate to each other.
Interesting, okay.
Okay, so summary, does it work? Kind of, but I think no one has actually fully clarified what exactly we're testing. So I think this kind of helps kind of give a bit more formalism to that and also gives a bit more formalism, like what test statistic to actually track here. Get a full auditor. And then, yeah, like passing an auditor also doesn't necessarily mean that the model is universally good. So you have to be very clear to yourself how good your auditor is. And that could be the human or an automated thing. And then if you're going to do this adaptive testing thing, probably use an e-process. But then because you're in this testing by vetting framework, you can do what a non-statistician told me just last week, which is go crazy. All right, so I think that's basically it. And I think obviously.
Most of the time, so if people have to go, feel free to step out. We're gonna take a couple questions for Jean.
I'm wondering, how do we factor in, the difficulty of the question that's being asked? But even with the, not the right question, I can imagine like some things being annotated being maybe easier to accept and maybe some things being harder than others being ambiguous. Like even something like, do I have family history of X, Y, Z? It's like a very clear yes or no. If I say, yes, my father has a history of cancer, maybe it's like harder to like say, well, sort of, because the only person that who I know who had this disease was like my paternal great grandmother, right? So it's like one doctor might say, yes, that's something that we need to account for, so you have family history, and then another doctor might say, well, no, the vaccine doesn't matter, or do you have previous drug use? I'm like, well, yes, I smoked cigarettes like 20 years ago, and then I stopped and had to clean for a long time. Different people might have different opinions about whether that's something they need to like check the box for yes or no. So then when you're doing that, right, is that like be something you're accounting for when you're assessing?
I think the current setup that we looked at doesn't, because it's using a uniform threshold to decide what is a failure mode. But I guess one way to adjust for that could just be for different subgroups. You have like required accuracy thresholds for that specific data set. But we haven't tried to do it. Be interesting.
I would ask this notion about good auditor.
So,
This idea of, give yourself a good auditor.
uh-huh,
Do you have any definitions around what that, think that might mean?
I've not figured that out.
Because there's some sense in which, like I'm thinking about, if someone built an LLM, they're more likely to know what its weaknesses are than someone who's completely naive to it.
Yes.
So I mean, like a good auditor is like somebody who knows.
Yeah,
It's a little bit like in anything you do, one of the reasons you bring in an expert is because they know what problems to look for. So
Yeah.
there seems to be some sense of like knowing what to look for makes a good auditor.
yeah. And I think like sometimes a human is better at being an auditor because they have that external prior knowledge and they're not just completely kind of subject to the amount of data they have in front of them. And sometimes maybe a automated thing that's actually trying to fit a neural network over things can actually be more powerful. I have not figured out how exactly you can test a priori if an auditor is good. That's what my students are trying to figure out, but it's tough.
I have one other question, which is so. Lately, we've been thinking a lot about auditing these things with real patient questions. So we've been doing a lot of work in this where we're like taking real patient questions and turning that into a rubric.
Yeah.
That then model applies. So it's kind of like LLM as a judge using a human generated rubric. Does that make sense? Like.
So the human is writing the rubric and the human gave you the question.
So the human gave you the question, so there's humans on that end.
Yeah.
And then the rubric is being written by a clinical fellow.
Oh,
It's
okay.
like saying like it
This
should
is
have
what
this or
this
should not have this. versus the human like being in the loop every time, trying to be more efficient,
Yeah,
so we
yeah,
can
yeah,
test a
yeah,
lot of
yeah.
different models.
Yeah.
Does that just like immediately put you in the first part of the talk or the second part of the talk, or have you thought about like where there's like
Yeah,
a human, expert human writing a rubric?
people have talked a lot about like, if you can write better rubrics, then like LLMs will judge better. So then you can trust it more.
But that would still be the LLM, sort of LLM judge.
Yeah, I guess it's
Yeah.
like, it's hard to check if your rubric is really working, so then I would put it in the first category. But I think if you try fitting something like the Bayesian model, or if you just get gold standard labels, you can kind of see like how much uncertainty there is and how much wiggle room there is.
Yeah.
The other thing that I ran across a paper last week that was saying humans are very bad at judging things on rubrics anyway. And what they're, and there's the other type of way of evaluating LLM, which is head-to-head comparisons, usually when you're trying to do relative ranking. And so you just take answers from one LLM and another LLM, and you just ask human, like, which one's better?
Yeah.
And so, I guess the point of the paper was like, rubrics have kind of like place an implicit assumption about what is better, and you tell people like, what does 1 mean? What does 2 mean? What does 3 mean? When you ask humans, like, if you just evaluate this in terms of like accuracy or safety, which is better or not, humans are much better at that. And so I don't know, like maybe we should all be doing relative comparisons.
Good. Any other questions?
I guess back to the first product. I guess I'm wondering if you were to imagine a setting when you had multiple LLMs to evaluate, I know you're just focusing on two, one you're able to evaluate. How do you think about like maybe assessing consensus between the answers of the different ones they're giving as some sort of gauge for whether they're giving a good answer or not? Because I guess I was thinking about like Margaret Pepe's Alzheimer's example, where like if you get the same medical diagnosis from like 10 different physicians, then you're going to think that they're probably correct. Whereas if you're getting a medical diagnosis from just one, it's hard to like get a sense of even if they're using a really good rubric, even if they really don't know what they're doing, you know, you might still want to get a second opinion, right?
Yeah. So we had 2 LLM judges, and sometimes people call the LLM as a jury. And then there are different ways to use this jury system. The way that we did in this paper is to average the scores, which is pretty common. The other way that people do is you have the 2 judges debate each other. It's very costly, but that is another way. The thing that worries me is because all of these LLMs are trained on the same data. And maybe they are slightly trained in slightly different ways, but I'm like, they can't possibly be independent. And I think there was one recent paper that was trying to actually kind of impart this view. I think it was like 9 judges, but the effective sample size is 2 or something like that. So yeah, that would be my concern.
Let's thank you very much for a lovely talk.
All